Hey guys, welcome back for part two. A little technical issue that causes part one and part two issues. So let's continue with another example. I want to find the lengths of the missing sides of the triangle. So we notice here we have two sides missing, whereas on the previous one we kind of had two sides missing, but we're only worried about one. So there's a couple ways we could go about this. If we knew one of the sides, if we knew two of the sides, if we knew one more of them, we could do the Pythagorean theorem. But we don't. So we are going to have to use trig functions to find at least one of these two sides that are missing. Once we found that side, we could then use the Pythagorean theorem to find the other. But it's more fun to do it with trig functions, so we're just going to go ahead and do that right now. So since we're looking at this angle here, it's 41 degrees, we know the hypotenuse. We don't know the opposite or adjacent side, so we're going to want to use sine and cosine to find these two sides. You could use sine to find, say, side A, and then use tangent and the side A that we found to find A and B. Or similarly, you could use cosine to find B and then tangent to find A. But it's just easier to use sine and cosine right from the get-go and find these two missing values. So we know that sine of 41 degrees. So let's just start fresh on that. Sine of 41 degrees is equal to, the sine is opposite over adjacent. So opposite here is, opposite over hypotenuse. Sine is opposite over hypotenuse. So opposite is A, that's our missing value. And our hypotenuse is 8. Similarly for B, we are going to use cosine of 41 degrees, and cosine is adjacent over hypotenuse. So we get this very similar structure for both of these two sides. Both of them are going to have the same first step, multiply by 8 on both sides. And what we end up with is 8 sine of 41 degrees equals A, and 8 cosine of 41 degrees equals B. Now, we're just going to grab our calculator. Again, making sure we're in degrees. So 8 times the sine of 41 degrees. That gives us 5.248. Now, how far out do we go with this? Well, a good rule of thumb is if no one else has said anything, 2 decimal places is pretty good. Okay, so we will go 5.25. Okay, and that is approximately. Okay, now we are just going to do the same thing, but instead of sine, we're going to do cosine, and we get 6.037. So we get that B is approximately 6.04 degrees. Okay, these are pretty simple, right? The hardest part with any of these problems, either this example here or this example here, is identifying what trig function you need to use. Okay, let's just do another example, right? So there's nothing better than just working problems after problems. So this is a tricky one. Now, it's not like scary or anything like that, but it's just a little special. So the angle of elevation from a point on the ground to the top of the pyramid is 35. You know what? I'm sorry. We'll talk through this. I don't want to do this. And like I've said this last lesson, I don't like these degrees and minutes. It's just annoying. So let me convert those real quick. So you know what? No. This is it's just messy. I'm not going to give you a problem like this with degrees and minutes. It's just unnecessary. But let's talk through how we would solve this if we want to deal with it. So the angle of elevation from a point on the ground to the top of the pyramid is 35 degrees and 30 minutes. The angle of elevation from a point 135 feet further back to the top of the pyramid is 21 degrees and 10 minutes. Find the height of the pyramid to the nearest foot. Okay. How in the world do I do it? Well, it comes to setting up a big system of equations. What we do is we can say let this distance here, let me do it with a color. This distance here, let that be y, and that's x. And so what we can get is we can get the equation that the tangent of 21 degrees and 10 minutes is equal to x over y plus 135. Now we can simply multiply both sides by y plus 135 to isolate for x. Okay. And this becomes a very messy algebra problem that I don't want you guys to have to deal with right now. I know I have it in here. I thought it was a little simpler when I was first putting it up here, but don't worry about it. What ends up happening is you get y plus 135 times tangent of 21 degrees 10 minutes equals x. We're going to distribute that tangent to give me y tan 21 degrees 10 minutes plus 135 tan of 21 degrees 10 minutes equals x. Subtract 135 tan 21 degrees 10 minutes from both sides. Okay. And then we get y tan 21 degrees 10 minutes equals x minus 135 tan 21 degrees 10 minutes. Divide by the tangent of 21 degrees and 10 minutes. I know you're like, what in the world? What are we trying to do? And that's exactly the problem with this whole issue. Okay. And so what we end up with is y equals x minus 135 tangent of 21 degrees and 10 minutes divided by the tangent of 21 degrees and 10 minutes. Now, why this is important is because what we can do is our whole purpose of goal is to find x. And we get that the tangent of 35 degrees and 30 minutes is simply x over y. Okay, so this was our goal. So I forgot to kind of mention that. Now we found y, but that's not the most helpful, except in the sense that we now have eliminated one variable. So I'll show you the kind of forethought of where this goes. Where this goes is then we substitute in this expression here for this y here. So we end up with the tangent of 35 degrees and 30 minutes is equal to x divided by x minus 135 tan 21 degrees 10 minutes divided by tan 21 degrees 10 minutes. Okay. From here, it's just a bunch of algebra to just isolate these x's. And quite frankly, it's so, well, for the lack of a better word, tedious and unnecessary. This is very similar to another problem that I've done in the past that was much simpler, and that's what I thought this was. So I apologize. Skip this. Let's go ahead and let's do that in nice big red. Skip. Okay, let's move on. So we're going to talk about some special triangles. What is a special triangle, you may ask? Well, there are 3 special triangles, okay? And when we talk about these special triangles, we're going to talk about them with kind of minimal side length, if you will. There are 2 of them are right triangles, and one of them is equilateral triangle. So we'll start with the equilateral. Which I'm very good at drawing equilateral triangles. Let's see if I can do a little bit better. Yeah, that's not bad. I'll take that. So an equilateral triangle, all angles are going to be 60 degrees. Okay, and all sides are going to be the same. We choose 2 here to make some calculations a little bit easier in a minute. Now, the reason why this is a special triangle is if I do this, making that a 90, I get this special triangle. Okay, and this is a 30, 60, 90 triangle. So this red line here in the equilateral triangle completely bisects this base, which means that this length here is 1. Using Pythagorean theorem, we get that this is simply root 3. Okay. If you're not sure, you can do the math on that using Pythagorean theorem and figure that out. So this is one of our special triangles. Another special triangle we have is this guy. And this is the 45, 45, 90. And if we let both of these sides be 1, this is root 2. Okay. So these are 2 special triangles. And the reason why they're special is because they give us the angles that we need to fill in, sorry about that, to fill in this table. Okay. So what's really cool, if you remember back to the very beginning, let's go all the way back. Let's zoom out a little bit, make it a little faster. We talked about these similar triangles, and we said that these ratio of sides were the same, right? It was the same no matter what, whether it was, whether it was the ratio within one triangle to 2 triangles, whatever it is. And so what made 2 triangles similar was that they had the same angle measure, right? So it doesn't matter how big these special triangles are. If they are a 45, 45, 90, or if they are 30, 60, 90, their trig function values will always be the same because that ratio will always simplify down to this ratio here. So that's a really cool thing. Now, this table is a little small, and of course I didn't type it in right. I typed it in right. And of course I didn't type it in, make it big enough for me to write in. But we can find these values really quickly. So let's first focus on a 30-degree angle. We're going to find our 6 trig function values for that. So that means we're going to look at this triangle here. And so for this 30-degree angle, our opposite side is 1, our hypotenuse is 2, our adjacent is root 3. Now, sine is opposite over hypotenuse, so that's 1/2. Cosine is adjacent over hypotenuse, so that is root 3 over 2. Tangent is, that's right, yes, yeah, opposite over hypotenuse, or opposite over adjacent. Man, I cannot speak. So I'm going to do something over here real quick. So that is 1 over root 3. Now, I'm okay with this on, especially like a test or anything like that. I'm not going to make you guys rationalize these, but it is something that's good to know. So typically in mathematics, putting a radical in the denominator is a frowned upon no-no for mostly simplicity and beauty. And so what we want to do here is we multiply this by root 3 over root 3. And in doing so, when we multiply fractions, right, we just multiply straight across. So we just multiply, let's go multiply 1 times root 3 and root 3 times root 3. And so 1 times root 3 just gives me root 3. Now in the denominator, I get root 3 times root 3. Make this not look like I'm subtracting. These are arrows. Root 3 times root 3 is just the square root of 3 squared. When we square square root, the square root goes away, so that just becomes 3. Wow, that's terrible. 3. So the tangent of theta, when theta is our 30-degree angle, is opposite over adjacent. So it's 1 over root 3, which rationalizes to root 3 over 3. Okay. Now, if you guys do put 1 over root 3, I'm perfectly okay with that. Mathematically speaking, they are equivalent terms. I'm happy with equivalent terms. Now, to find cosecant, secant, and cotangent, what do we need to do? We just remember they're paired up with other ones and flip them. Cosecant pairs with sine, and so we flip sine and we just get, hey, that's 2. Secant is cosine, pairs with cosine, so we flip that, and now we're going to have to do that same rationalizing thing. So what we end up with 2 root 3 over 3. Okay, and tangent of theta pairs with cotangent, we flip root 3 over 3, or if you think back to what we started with, it was 1 over root 3. Flip that, and we just get root 3. Okay, it's not too bad, right? Now, what's cool with the 45 is it doesn't matter which of the two angles we pick in that 45, 45, 90 because they're the same thing. And so what we end up with is for both our sine and cosine, we end up with 1 over root 2, which rationalizes to be root 2 over 2. That's cool. So the cosine and sine are the same thing. And if we flip that, we just get root 2. So that means cosecant and secant are both just root 2. Now, tangent of theta is opposite over opposite over adjacent, which is 1 over 1, which is just 1. Flip 1, and you get 1. That one's pretty cool. I like that one. So, what about 60 degrees? Well, if we look up there, the opposite side is root 3. The adjacent side is 1. That's really similar to the 30 degree, right? The 30 degree was the other way around. It was opposite was 1, adjacent was root 3, which means that sine of 60 is opposite over hypotenuse. That's root 3 over 2, which that was just the sine of 30. So because these 30 and 60 are in one triangle for 90 degrees, their opposites and adjacents just flip, which means sines and cosines flip. So it means sine of 60 is root 3 over 2, and cosine of 60 is 1/2. That's really cool. Now, what about tangent? Well, tangent is opposite over adjacent. And if the opposite and adjacent sides flipped, that means that it's just which means it's just the cotangent, which means that's just root 3. Now, you can do the same thing with our secants and cosecants. 2 root 3 over 3, 2, and then this is root 3 over 3. Now, there's a lot of shortcuts I took in there, a lot of things like, oh, notice this, notice this. I'm hoping that you guys are comfortable setting up these ratios. If you just went through and brute force did it, 60 degrees, sine of 60 degrees is opposite over hypotenuse, so that would be root 3 over 2, and bam. So I'm hoping that you guys get that. I wanted to use this as an opportunity to kind of show some of these cool relationships that happen in here and kind of talk about those. So now we are going to get some co-function formulas. And that's kind of what we got at with that 30 and 69 degree triangle. Sine of theta is the same as the cosine of 90 minus theta. So notice that 60 is just 90 minus 30. And so we get these really cool relationships going on here. And the same thing follows for cosecant, and cotangent, and all of those things. And so this is a really kind of cool thing. This would be something that if you are creating a formula sheet, would be a good idea to use. So what I highly recommend as this class goes is you should have a separate page. Maybe it's the back of your notebook, or maybe it's just a separate white sheet of paper where you're going to write down formulas and identities as we get to those and things like that. Things that are really kind of would be like something you would put on a note card. So kind of as we're going through this term, you're building up this note card. Here's something you should put on that note card. Okay, sine is opposite over hypotenuse is something that you're just going to know. It's not something you should have to have written down. If you want to, it's fine. Doesn't mean anything. But this is definitely something you're going to have written down, because this isn't really something that you're going to memorize. If you have that kind of a memory, that's awesome. I don't. This is something that I have written down for myself. So using that, let's think about writing some equivalent expressions using these co-functions. So cotangent of 23. Well, that is cotangent. Okay, if we look back at our table here, use Galaxy pen. Cotangent of theta is paired with tangent of 90 minus theta. So cotangent of 23 degrees is the same as the tangent of 90 minus 23 degrees. I want to erase that, do it a little smaller so I don't quite overlap with B. So cotangent 23 degrees is tangent 90 minus 23 degrees. That's better. So that's equals. So that means cotangent of 23 degrees is equal to the tangent of, what is 90 minus 23? 90 minus 23 is 67. So that's the same as tangent of 67 degrees. That's pretty cool. All right, I want you to pause this video and do these next two by yourself, okay? Don't let me get in your way. Go ahead and do these by yourself. Come on, come on. This is the end. This is like, we're almost done. You can do it. All right, let's do them together. Okay, and if you did them, awesome. Good job, welcome back. So secant of 70, I'm gonna jump down here. So secant of 70 degrees is equal to. So if we look up here, where's secant? Secant theta is cosecant of 90 minus. So that is equal to cosecant 90 degrees minus 70 degrees. So that means secant of 70 degrees is equal to cosecant of 20 degrees. Nice, this is really easy. Cosine of 12 degrees is equal to, where's cosine? Cosine is sine. Cool, cosine. So that's sine of 90 degrees minus 12 degrees. So cosine of 12 degrees is equal to sine of 78. Look at that. I didn't like those equal signs, and that was too big of an erasing. So that's a way we can use cofunctions. That's pretty cool, right? So big takeaway from this lesson is the definition of sine, cosine, tangent, cosecant, secant, and cotangent, and what their relationship is within a right triangle, how to find those. Okay, and being able to do problems like angle of elevation, angle of depression, these kind of problems, not this kind of problem, these kind of problems. Okay, being able to do these kind of problems is a very kind of important, useful task, skill that you will use for this class. Don't forget angle of elevation, angle of depression; those are slightly different. And then this table here of these special values will come back to us in a little bit. We will definitely be using these values, especially sine and cosine. And when we do use those, you'll be like, oh, hey, those are the special values. We used those before. All right, you guys, that's it for lesson for 6.2. I'll see you guys next time for 6.3.